Hello, this is Dr. Mode, and welcome to chemistry class today. Today we are moving on to the next section, section 4, and we will be calculating enthalpy change. Our scripture verse for today comes from 1 Peter chapter 4, verse 10. It says, "As each has received a gift, use it to serve one another as good stewards of God's varied grace." So here's our progress so far through chapter 15. Again, we've finished section 1, 2, and 3. We're starting section 4 today, and then we're going to do section 5, and after that we're going to have our chapter test. So the essential question that we're going to focus on for today is, how is Hess's law applied to calculate the enthalpy change for a reaction? So certain chemical reactions occur in extreme conditions, or they are just messy, and it is very difficult to measure heat related to these reactions. So there is a way to calculate it, okay? So Hess's law states that if you can add thermochemical equations together to produce a final equation, then you can also add their delta H's together. So one of the equations that's kind of messy is the equation that produces SO3 gas. So the question we're going to look at is, how can Hess's law be used to calculate the energy change for the reaction that produces SO3? So the reaction we're looking at is 2 sulfur plus 3 oxygen gas goes and produces 2 SO3 gas. And we want to figure out what its delta H is. The reason we want to do this is because if you try to run this reaction, the reaction is messy. There are other products that are formed, other reactions happen, like there's a lot of SO2 that's produced. So because we want to focus on this reaction that just produces the SO3, what we need to do is use Hess's law. So there's some other information that is available. That available information is that there are 2 equations where delta H is known. The first one involves the products that we see in the blue reaction, the S and the O2, but it goes and forms SO2 instead of SO3. That's equation A. Equation B has SO3 involved in it as a reactant instead of a product. So both of these have delta H's that can be measured in the lab. So this is where we're going to start, step 1. So we're going to use equations A and B and try to see if we can get this equation that's up at the top here. So equation A involves a sulfur atom, but the equation that we want involves 2 sulfurs. So what we can do is we can take equation A and we can multiply the entire equation by 2 to come up with a new equation, equation C. So equation C now has 2 sulfurs at the beginning of it. Now what we do with delta H is we can apply Hess's law here. If we can multiply an equation by 2, then the delta H can be multiplied by 2. So this new equation, the delta H, is now twice as large. So now what we're going to do in step 3 is we're going to look and see if we can use equation B. So here's equation B. Equation B had SO3 as one of the products instead of one of the reactants. But what we can do is we can look at this and see that, that it also has O2 on the other side. So what we can do is we can reverse this equation. We can change the reactants and the products. So what we're going to do is we're going to write a new equation, equation D, which is just the reverse of equation B. So here now we've swapped the reactants and the products, and when we do this, what's going to happen to delta H is also going to change sign. So now we're at step 4. Step 4 is the final step. And what we can do is we can see if now we have enough information to be able to derive this equation at the top of our screen here. So what we can do is we can add equation C and equation D together to achieve that. So here's equation C and D. And if we add these together, what we get is this right here. And what you'll notice is that it has SO2 on both the reactant and product side, and those can cancel out. And when we do that, we are left with the equation that we were trying to get. So now, if we want to get delta H, what we have to do is we have to add. Since we added the thermochemical equations together, we can add the delta H's. So if we add negative 594 and negative 198, then we end up with negative 792 kilojoules as our answer.